All right. So we're going to be talking about phase diagrams, a triple point of water. And you're probably wondering why are we talking about phase diagrams? Why are they important? Well, for being a chemical engineer, we work under certain conditions that we're given, and we have to somehow think of a way to construct maybe a new product or something that will work under those certain conditions. Say we need to make something that will work to contain a certain pressure or temperature, and we can refer to a phase diagram to see where our uh, fluid, I guess in this case, what state it'll be. So here I have a water bottle. I don't know if you can hear that. Has some water in it, but you can't see it, obviously. And with this water bottle, I'm going to show you how to apply it to a phase diagram. And right now, there's some water in here, but there's also air in here. And that's going to be important because right now, in this system with water and air, we can't exactly apply that that phase diagram as of yet. And that's because there's air. There's not just water. And what we want to do is get rid of that air, push it out, and just have water in the system. Now, there's a lot of ways we can do that. We can fill up the water as much as we want, all the way up to the container until it's full, so it's just water. But that's not our goal. We want to reach the triple point. And what is the triple point? The triple point is the point at which, on the phase diagram, when all three phases, solid, liquid, and gas, are present. So right now we have water and air, but we also have vapor because the presence of water means the presence of water means that there's water vapor. And with that water vapor, we can use that to push out the air. And how are we going to do that? Well, let's move to our phase diagram right here. Now, say on our phase diagram, we're somewhere on this line, or we want to be somewhere on this line. Maybe right about there, since we haven't reached a critical point, which I'll be talking about in another video, but we also haven't reached a triple point. So we're somewhere around here, and we want to be able to apply this to our water bottle. So to do that, like I was talking about earlier, we need to push out the air. And how do we push out the air? Well, we have water and water vapor. The water vapor we can actually use to push out the air because, as you know, there's something called the boiling point, and at the boiling point, that is when the water vapor's pressure is equal to 1 atmosphere. So I have this system where the air and the water vapor right now, as I've opened it, are equal to 1 atmosphere. So the pressure inside, both the partial pressures of the air and the water vapor are equal to 1 atmosphere. And in order to get the air out, we need the water vapor to be equal to 1 atmosphere. That is the definition of the boiling point. And we know the boiling point is uh, is at the temperature of 100 Celsius. Uh, 100 Celsius. That is the temperature at which um, the water vapor's pressure is equal to 1 atmosphere. So, all right, say we heat this thing up, we get it all the way to 100 Celsius, and it's at the boiling point. Great. Now the water vapor is equal to 1 atmosphere. What does that do for us? Well, it pushes out the air. Why does it do that? Well, right now I just said it was equal. Both the partial pressures of water vapor and the air were equal to 1 atmosphere. So, in increasing the water vapor's partial pressure to 1 atmosphere, that makes it so that the air has to go out. If they were unequal, then some of the air has to go out in order for the entire system to be equal to 1 atmosphere to the current surroundings in the room. I'm going to say that again. The 1 atmosphere is equal to the system right now, which hasn't been boiled yet, with the partial pressures of air and water vapor. I'll just write it down. How about that? The partial pressures of the system is equal to 1 atmosphere, where we have the partial pressure of water vapor plus the partial pressure of air. That is equal to atmosphere. and then in increasing that partial, in increasing the partial pressure of the water vapor, we have to get rid of the air until this entire thing is just equal atmosphere. The air leaves the system, and finally we are left with just our water vapor in the system, which is equal to 1 atmosphere. I don't know how many times I've said 1 atmosphere. Okay, great. So we're at the boiling point. There's just water vapor and liquid water in here. Now we're on the curve. Cool. So how do we get to the triple point? Well, the triple point is the point at which on this graph you can see it is where the solid, the liquid, and the vapor are all present. Solid, vapor, and liquid water are all present. So right now we're on this curve. We're in equilibrium with liquid and vapor, as we know in the system. Liquid and vapor, that's it, since we push all the air out at 100 Celsius. So in order to go back to the triple point, or in order to head towards the triple point, we need to somehow decrease the temperature to make it so that there's solid present. And you can actually do this in your house. It's actually pretty simple. So once you've heated this up on the stove or something to 100 Celsius and you just have liquid water and vapor, you just stick it in the fridge. It's that easy. We stick it in the fridge and cool it to the freezing point. The freezing point where? Freezing point at 0 Celsius. And as far as I'm concerned, most fridges go past this, even to the negatives, like negative 20 or something, whatever it is for meat. But yeah, it's just sticking in the fridge. It's that easy. And putting in the fridge, we'll put it to the freezing point, probably past it if you leave it there further, in which you'll go past the triple point, and then maybe you'll just have solid and vapor. But just getting to the triple point, we'll have frozen some water. So we have some solid, the ice. We have the water vapor right here, vapor as a gas, and then liquid water. Cool. We reach the triple point. And it's just that easy. We just go to the triple point using our fridge after we heat it up, add liquid water and water vapor in the system, stick it in the fridge, and now we have some ice. Boom, we got the triple point. And actually going further, like I just said, we'll have, if we freeze all of the water, we'll have ice and vapor, making us go past this to the temperature, past the temperature for the triple point. Probably lower temperatures if you leave it there for, say, another day, a month maybe. All the water will have turned to ice, but you'll still have liquid vapor. So you'll still be on line. Now, what's probably important to discuss is the pressure. And the pressure where you'll be decreasing the pressure along with, as you move down the curve, along with the temperature. So say we were at 1 atmosphere right here, 1 atmosphere, will actually be decreasing as we go down. And the pressure will decrease until it's basically, we'll know it is less than 1 atmosphere going down the curve. And just reading the points, we go down 1 atmosphere, 100 Celsius, down, 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 triple point, 0 Celsius for the freezing point. And the pressure has to decrease. And that is how we use a phase diagram for reaching the triple point with water.